So we may be expecting less people today because it's a review session, not a full lecture, but how are you guys feeling about the exam? Next question. Are you prepared? Anyways, so let's discuss what we have covered. We have just covered the Euler-Bernoulli beam theory. The exam would mainly focus on whatever you have covered minus the deflections and torsion. So there won't be any deflections on the exam. But sometimes it's good to just know them, just so that you know what's going on in Euler-Bernoulli beam theory, because every concept is tied together. So for the exam, you should be able to remember what you have done so far in Euler-Bernoulli beam theory. How did we formulate the beam theory? What are the key points which makes the theory an Euler-Bernoulli beam theory? How do you simplify the complex continuum mechanics problems into simplified beam theories? You should be able to solve for the bending stiffnesses. You should be able to identify the centroids, the sectional centroids of a cross section. For a given loading, you should be able to understand what is the sectional moments and forces, sectional forces, sectional force resultants, sectional moment resultants, which you can apply on these problems to obtain stresses or locations for maximum stresses. You should be able to solve for neutral axes, for principal axes of bending frames, and basically you should have a good idea on what's going on in those small concepts and how they are interrelated. So we can do a few examples today, or we can just do one example. It depends on how we proceed throughout the entire lecture. If we are on a good pace or a good speed, we can probably look at more examples, but if we are slow, then we'll cover a few and then I can probably post the rest of them through Canvas. So I will try my best to go through this document as detailed as possible, but if there is anything at any point you think that you don't understand or you don't feel that it's correct, then just let me know. We'll then go to the board and try to figure out some things. Otherwise, I'll make use of the board whenever I feel like. So there is a cross section we have for the beam. This cross section has two materials, two materials, one with Young's modulus EA and one with Young's modulus EC. There is something different in this problem. The thickness of these two layers is not same, right? So if it was same, the centroid would have been the geometric centroid of this section, but it's not same. So the geometric centroid of this section will be different as compared to the sectional centroid we evaluate for our calculations, right? But I have a quick question. Where do you think, or what do you think the value of H23C would be?
0.
Why do you think it's 0? Okay, so there is an axis of symmetry about I2. So if you see this axis, this section is symmetric about that axis, so H23 is going to be 0. So in this problem we have some dimensions. B is 100 into 10 raised to the power minus 3 meters. H is 200 into 10 raised to the power minus 3 meters. Similarly, we have TC1, TC2 values given here. Then we have Young's modulus in pascals for both the materials EC and EA. We have the sectional force resultants and moment resultants given to solve the problem. So we have N1, so this section would undergo axial stresses, and we have M2, so this section would undergo axial stresses induced due to bending, right? So we have two components of axial stresses, one because of the axial sectional force resultants and one because of sectional moment resultants. Does everyone understand that? How do we have only axial stresses? Okay, so let's evaluate the sectional properties. So first is centroid. Let me just draw the cross section here so that we have information about the section. So this thickness is TC2, this thickness is TC1, the distance, the height of the entire cross section is given as h. The distance from the centroid to the top surface is x2c. The Young's modulus for this is EC. Then this material is EA and EC. Okay. So how do we evaluate the centroid? There are multiple techniques as we have studied. Either you calculate S2, S3 and divide that by S, which is just the integration EDA, or this is a fairly simple cross section. It has a bunch of rectangular areas merged together to make a composite like section. So we know the area for the bottom layer, we know the area for the middle layer. We can calculate by using these dimensions. And we know the area of the top layer. Also, this section is comprising of rectangular sections. So we know the sectional centroid for each of those layers, right? The sectional centroid for this layer would be at TC1 over 2 from the bottom part of this layer. Then the sectional centroid for this middle section will be at the midsection somewhere either up or down as compared to the sectional centroid of the entire section. And then similarly we have the sectional centroid of the bottom layer at the geometric center for the cross section, right? So we have that information and we have the areas. So we can calculate x2c, the centroid, by summing up all the areas with their x2 values. But before doing that, we need to take a reference frame, right, from where we are trying to calculate the centroid. We will do all the calculations in the centroidal reference frame for the bending stiffnesses, but to get to that frame, we need to have one reference frame to start with. So to start with, I'm taking a reference frame which is at the bottom and which is at the center, or which is at b over 2. So from this edge, it is at b over 2. And why I'm choosing at b over 2? Because the section is symmetric about that axis. So conveniently, I know for the sectional centroid, x3 is going to be 0, right? So I'm taking my initial frame of reference as this, just to start with, to identify what is going to be the value for x2c. And then I use this to evaluate my x2c. Okay, so when we expand this expression, we will obtain like 3 terms on top. One is EC times AC1 times TC1, which is for the layer, which is for the top layer, and then EA times A1 times TCL plus D over 2. Okay, for this, I think this expression is, yeah, yeah. So the X2C is measured from here. So I think everything is from this, I think. Yeah. So my frame is attached here, the initial frame. So it doesn't matter where the frame initially is, I will get the X2C value accordingly. But it's just that I want to be consistent with this notebook so that when I share it with you, there is no misconception about what the coordinate frame is. So then TC1 over 2 is the distance from the coordinate frame to the first centroid. Then this TC1 plus D over 2 is the distance to the second layer centroid, and H minus TC2 over 2 is the distance from the top surface to the distance of the third centroid. Here D is just the height of the middle layer. So H minus TC1 minus TC2, that's D. So when we evaluate that, we get a value 0.102799, and we know that H is 0.2. So H is 0.2. H over 2 would be 0.1, but our centroid X2C is at 0.102799, right? So it's not exactly at the geometric centroid of the section. This value is for the sectional centroid, which incorporates material properties. Any questions? Okay, so now we have N1, which is non-zero. We have M3, which is non-zero, but we have M2, which is 0. Okay, and we know that there is an axis of symmetry, and we are calculating everything in the centroidal reference frame. So we have H23 is 0, right? If H23 is 0, we can simplify our stress expression and use the expression sigma 1 is equal to E times N over S minus X2 M3 over yeah. H23 is 0 because we have one plane of symmetry. So about I2 there is symmetry, so it becomes an odd function. H23 integration will go to 0, right? So we can use this formula only. Yes, go ahead.
So does the problem sit with no M2, or do we like assume that? Why is there no M2? Or why, yeah, why is there only, why is M2 equal 0?
Because we have only N1 and M3 given in the problem.
Okay, that's
Yeah.
the problem thing.
Yeah. So we do not have any M2.
Okay,
Yeah. So we can use this expression only when there is a plane of symmetry, so that H23 goes to 0, or we are in a principal axis bending frame such that H23 goes to 0. So if the cross section is such that there is a plane of symmetry, H23 will go to 0, or if there is a principal axis bending frame and no symmetry, then H23 again will go to 0, right? So this formula can be used in that frame, or if there is a symmetry. So we have the value of E probably for each of these layers. Then we have M3, we have N1, but we don't have S and H33. So we need to evaluate those. And we are doing that by standard formulas that we have and not by using integrations, because we have a simple cross section which has rectangular areas. If we had something strange, we may use integrations, find out an infinitesimal area and try to integrate it. In this case, because it's a rectangular area, we already know the standard bending stiffness formula for a rectangular area about its centroid, and we can use the parallel axis theorem, right? So for calculating the bending stiffnesses of the first area, which is the top layer, this is the expression where 1 over 12 BT times BTC1 cube is the bending stiffness about the centroid of that layer. Now we need to apply parallel axis theorem, so we'll multiply it by area times the distance square. So area is B times TC1 and the distance is x2c minus TC1 over 2. So we are calculating H33 in this I2, I3 reference frame, and the distance from the centroid to the centroid of that layer is this distance x2 minus half of the thickness of the first layer. So x2 minus TC1 over 2. And we are taking the distance which is perpendicular to I3 and parallel to x2, I2. That is because we are calculating H33. If we are calculating H22, the distances you would take would be parallel to I3, perpendicular to I2, right? These distances are not absolute distances. The centroid could be here, but still you would take the distance which is parallel to I2 for H33 calculations, right? You won't take the distance which is the absolute distance. So then we will calculate this H33 for the middle layer, which will be 1 over 12 B d cube. D, as you remember, is the height of the middle layer, H minus TC1 minus TC2. So this is the H33 about the centroid of the middle layer. Now we will use the parallel axis theorem. So it becomes A1 times x2c minus TC1 minus D over 2.
Do we need E's? If this is H, isn't there an E, or did you just like leave the E at, like, is there a reason you're not putting E in there too?
E, the value of E?
Yeah.
Yeah, so that's, yeah, I mean, the value of H will multiply E with it, but I just focused on the moment of areas.
Okay. Thanks.
And then we have the third layer, which will again have material EC, and then 1 over 12 B times TC2 cube. This is the H33 about the centroid, and then parallel axis theorem. So the area of that layer times x2c minus H plus TC2 over 2. And then we will add all these expressions, because we know that the sectional bending stiffnesses are additive, so we can just add all of them for each individual layer. And we can add them because we calculate each of these quantities at a common reference frame which is associated at the centroid of the section. If we are not considering the centroid of the section, we cannot add them. We have to make them or calculate them in one reference frame before adding. So now it's a simple exercise to evaluate stresses. We have axial stress due to the axial loads in this term, and then we have axial stresses induced due to bending in this term multiplied by the material properties. So each of these materials will have different stresses because of different Young's modulus values. So we will evaluate stresses in each of these layers and then plot them. So this plot shows stresses due to N1, so the axial load. We know that when axial load is applied, the stresses are constant, but they are different in different layers. So from minus 0.1 to somewhere at 0.3 or 0.7, yeah, because the thickness is about 0.03. So 0.07, so from minus 0.1 to minus 0.07, you have the first layer, the thicker one. Then you have the middle layer, which is the thickest layer, and then a thin layer at the end. So this shows the actual stresses plot with x2. So as you go up from the bottom, how the stresses are due to N1, and then the stresses induced by bending are always linear because we have a term associated to x2 over here. So this is a linear term. So that's why you see a piecewise linear plot for the stresses induced due to bending. So if you have to plot stresses along x2, you can just plot the values in each of these layers, and this will be your plot for stresses induced by M3. And then if you add them together, so this is the total stress induced by this problem. Yes?
For the N1 over S, is it S for the whole section?
Yes. Calculated at the centroid.
Okay. So like sigma 1 in the top layer would be the EC times the entire N1, the entire like axial load applied over the...
Yes, yeah. Because this quantity represents the strain, and that is calculated for a section. And then you multiply it with the material property of the layer to identify the stresses in that section.
Can you go over calculating the actual S value?
Yes.
What's that again?
So calculating the S value,
Okay.
so this is what you used in the denominator for calculating the centroid, the sum of all the product of the material properties times the area. So if there was only bending, because we have a sectional symmetry, if there was only bending, the stresses are 0 at x2 0. But if we don't have just M3, we would have this value shifted to some other distance, right? The stresses are 0 at some positive value of x, means the neutral axis has shifted a little upwards because of the application of an axial load. Any questions? Okay, so can neutral axis be present outside the cross section?
Yeah.
Okay. So can we move on to another problem? A different one? Okay. Yes, go ahead.
For the neutral axis to be outside of, if you have like a rectangular cross section and you have like, I don't know, like an M2 and some axial force, like your axial force has to be pretty high for the neutral axis to be outside of the
Yeah.
thing, right?
Right. So you have to apply a axial load in such a way that this point shifts beyond the domain of your cross section, and then yeah. And that how high the axial force would be would be governed just by this analytical expression. If yeah, if x2 value is in if this expression is 0 and x2 goes out of the domain of the cross section, means you have neutral axis which is outside the cross section. So this expression governs kind of where the neutral axis is. Yes.
Why did you say the axial stresses due to the bending moment are 0 at the origin? Like if you show the axial stresses due to the bending moment, like pure bending moment, why did you say it was 0 at the origin? Is it because of the symmetry, or is it because of we are considering it with respect to the centroid?
We are considering it because of this at the centroid. Yeah. So if we are in the centroidal reference frame, then it's 0 at that axis.
But it has nothing to do with the symmetry, right?
Has nothing to do with the sectional symmetry. Yeah. I said the symmetry thing because it makes H23 go to 0.
But it's still gonna cross the origin, right? Because it's x3 times something and x2 times something.
Right. Yes, but here we are looking only at x2, means we are looking at all the values of x3.
Right.
So,
Sure.
yeah.
x3 doesn't play any factor because
In
x2
this,
is 0.
yeah, in this
Yeah,
problem, yeah. But if there was no symmetry, then H23 would have been positive or some value, and then this expression would have
Another term.
terms,
Yes.
and they have x3 in it.
Sure.
So then we cannot say whatever I said.
Yeah.
That's why I had to say that, because it's symmetric, x2 will go to 0 for all the values of x3.
Thanks.
Okay, so let's move on to another problem. Let's look at this section. So this section is now not symmetric. So what should be the value of H23? 0, non-zero? Non-zero. Okay. So we will do the same thing. The steps remain the same. First we choose a frame of reference using which we will calculate the centroid. Then we evaluate the centroid value and put a frame there, using which we will calculate all the bending stiffnesses, right? So first we evaluate the centroid. It comes out to be somewhere here. Attach a frame to it, and then evaluate all the bending stiffnesses. Again, let me just draw it for your reference. And this is H, this is thickness T, and then we have A and B. So we have these dimensions B, H, A and T given some value. I'll post them on canvas so that you can go through this file again. And then we have Young's modulus. So this is not a composite section, it is just made of one material, but there is no sectional symmetry. And then we have a transverse load of P applied at the end, and that's given here, such that the length is 4. So length of the beam is 4 meters, and then there's a 4,000 Newton load applied on it. So we have to determine the maximum bending stress for M3 due to P. So we have to calculate sigma 1, bending, stress induced due to bending, and we have a shear force P applied at the end. So we have to identify this expression is now not going to have just H33, it will have a component of H23 as well. So we have to identify that and then solve the problem. So the steps remain the same. First we evaluate the centroid, which is being done here. And as we know that there is no plane of symmetry, so we have to evaluate both x2 and x3. Right? We cannot make any judgment on where x3 should be. So here we evaluate x2 and x3. Then we calculate the bending stiffnesses h22, h33 and h23. And we do this by dividing this cross section in two areas. So we have one area which is smaller one and the second which is larger. Now these have sections of symmetry in individually these areas. So we know that the centroid of this section, because it's isotropic, no composite, so the geometric centroid is going to be the sectional centroid for this subsection, and then the geometric centroid for this is going to be the sectional centroid for this subsection. So we have two independent centroids in this problem. So we can evaluate the bending stiffnesses of this subsection about this point, which is the centroid of this section. We can evaluate the bending stiffnesses of this bigger section about its centroid, and then use parallel axis theorem. So when we calculate H22, as we mentioned, we take the distances which are parallel to I3. So for the first section, the distance from this coordinate frame will be this distance. So this is the distance for parallel axis theorem application for calculation of H22 for this first subsection, and this is the distance which is going to be for the second subsection. Right? And if we are calculating H33, we take the distances which are parallel to I2. So H33 is the sectional bending stiffness about I3. So the distances that matter are perpendicular to I3. The distances which are parallel to I3 do not matter because they do not induce that stiffness. Okay, so I would skip these calculations, but you can, yeah, go ahead.
What about, how do you use the parallel axis theorem for H23?
So for H23 is similar. If we have look at the expression, it's integration E x2 x3 dA, right? So now when I'm trying to move to a different coordinate frame, I would have to transform x2 and x3 to match to that coordinate frame, right? So I will get H23 is equal to integration E x2 star plus x2c times x3 star plus x3c. If you remember the same configuration we had in class in the lecture when we are moving from some coordinate frame to the centroid, right? And then we have dA. So what I'm doing here is, if I have a cross section, the cross sectional centroid is here, I2c, I3c, and then I have this reference frame, I2, I3, and this distance is x2c, x3c, and then this distance is x2c. So this is my configuration. Yeah, go ahead.
Does it matter when you're doing x2 star plus x2c? Does it matter if it's plus or minus in there? Does that matter?
It matters where you are going. Like you are coming from the centroidal reference frame, or you are going to the centroidal reference frame. So, but the thing is that if you are taking centroidal reference frame, then the terms which actually govern the sign, they go to 0 because they become an odd function. So it would matter, yes, if you are not considering any movement to or from centroidal reference frame. If you're dealing with centroidal reference frame, the sign won't matter. You see why I'm saying that? I'll come back to that point again. So now we just have to multiply these. So we get integration e x2 star times x3 star plus x2 star times x3c plus x3 star x2c plus x2c times x3c dA.
Would it be dx2 star or dx3 star?
Where is the d coming from?
When you replace dA, would you replace it with dx2 star or dx3 star?
Would that change? Because x2c is a constant, so dx2c will go to 0. So yeah, you can just write them dx2 star, dx3 star. Yeah. Because yeah, the differentiation, a small element would be here, and this is constant, so d of that it goes to 0 because that would be constant, right? So yeah, you can say dA star. So now this term is your h23 star. Then you have these terms whose integration will go to 0, right? Yeah.
So what are these stars? Doesn't star mean principal axis?
So I already wrote, I'm considering the centroidal frame to be the star one here.
Okay, and then the original thing
Is normal x2, x3, the no star. Yeah. So I'm doing this transformation for this subset, a small problem, just to show the derivation. And we have two coordinate frames, I2, I3, and I2 star and I3 star. And the distances are x2c and x3c. And I'm assuming that this I2 star and I3 star is a centroidal reference frame. But I'm not talking about any principal axes of bending in this problem.
So x2c is the location of the centroid force and the centroidal reference frame.
Yes.
And x2 star is what?
X2 star is a coordinate in the reference frame I2 star and I3 star. So,
Okay.
so for example, if I have a point here, I can give the identity of this point either by using the starred frame or by the normal frame, right? So in the normal frame, its coordinate would be x2, x3, but in the starred frame, its coordinate will be x2 star, x3 star. So if you see, this point will have x2 coordinate, which is equal to x2c plus x2 star.
Okay.
So x2 star is just a coordinate.
Okay. Thank you.
Yeah. So yeah, go
Is
ahead.
there a difference between dA and dA star?
There is.
Translation.
Mhm.
Then the dx it would be equal to dx star, right?
Yeah, but the thing is that
You're not changing the reference.
if I'm changing the reference, the limits change.
Oh, we are both changing the reference and then changing the variable also.
So what it essentially means is that I'm changing the limits, right?
Sure.
That's all. I have to be consistent with every step I do. So if I have dx2 here, the limits are different, and yeah. So now the integration of these two quantities will go to 0. Yeah, go ahead.
Is it like using the axis parallel theorem, like what you're doing?
Mm-hmm.
The same for H2?
Yeah,
Okay.
yeah. The question was how the parallel axis theorem would work for H23. So I'm just trying to derive an expression for parallel axis theorem for H23. So yeah, these we already figured out this term, which is H23 star. These two terms would go to 0 because they are an odd function. So now coming back to your question, that if there was a negative sign here, probably some of these terms would face the negative sign, but integration of that is going to 0 because we are dealing with the centroidal frame of reference, right? So that's why these go to 0, and we are left with this, which is in simple terms integration EdA times x2 x3 x2c x3c. They are the distances d2 and d3 which we generally refer to as. So it becomes h23 star plus s times d2 and d3. So let me rewrite this equation here.
And H23 star is with the original coordinates?
So H23 star is from some point you are trying to bring the H23. So what you are calculating is H33, which is in this frame. So you first calculate in the centroidal frame, and then you are trying to bring it back to this reference frame.
Yeah, okay.
So H23 star is about the centroidal frame. So that's what we do in these problems. We have this subsection, we have the centroidal frame. So we calculate H23 there, use this formula to get to that frame where we want to go. So this is going to be the final representation, just in case if you are not able to see that. Okay, so we will calculate all the values for H22, H33, H23, and then we will compute delta H, which is H22 times H33 minus H23 squared. Yes.
Waiting for H23, D2 and D3 are equivalent to X2C and X3C.
Yeah, so they are basically the distances which I'm traversing in I2 and I3. So if you look at this section, when we have to calculate H23, I need a product of D2 and D3. So D2 would be this distance. In I2, D2 will be this distance and this distance, and D3 will be this distance and this distance for different subsections. So I'll do that individually. For this section, I'll calculate H23 and then I'll move it here. So D2 and D3 for this will be this height is D2 and this height is D3.
Okay.
Right? Yes.
Usually H23 star will be 0, right? Is that true? Because there's symmetry around each individual shape.
Yeah. So H23 star for this subsection is going to be 0. Yeah. And then there will be a non-zero term. Okay, so we will calculate delta H just for our simplicity. The stress expression in this problem is going to be this long expression. Let me see if I can zoom in. Yeah. Because we have now H23, so we would have to take both of these terms into account. And then so we were given a load of P which is applied at the tip. So we have to evaluate the sectional bending resultants, the sectional force and moment resultants. So we resolve them to be 0 and P L minus x1. Any questions about that? Just making a cut in the beam and evaluating what is the moment at that section. And then we are just substituting those values in the sigma expression which we wrote here to determine what are the stresses. So here the points are A and B. A is the point at the bottom and B is at the top. So we evaluate the stresses at both A and B, and we get the values. It seems like at B the stresses are the highest. So yeah, any questions about sections which do not have symmetry, non-symmetric sections? Yeah.
Are we allowed to bring equation sheets, or do we have to just memorize all that?
Yeah, you can
So
bring
notes.
one page of cheat sheet which has letter-sized equations or text typed up and single spacing. Yeah, and then you have to attach it with your exam.
Can we handwrite it?
You can handwrite it, yeah, but make sure it's not too small. Yeah. I don't think there are too many formulas. Yes, go ahead.
What is that, right? Not 2 sides?
Check out the syllabus for that. Yeah, I think it's one-sided, but I would check the syllabus. Yeah.
Are there any restrictions on calculators?
Normal standard calculators. I don't know the codes. 991 ES, the scientific ones, they are okay. Yeah, but not the ones which can store the formulas beforehand. Yeah. No computers. Yeah. Do you want me to bring some papers for you to write on? Okay, I'll bring some papers so that you don't have to bring. Any other question about the exam? Okay, so I would like to just go over through the tip deflections for this too, because we have a couple of minutes. So if we have to evaluate what are the tip deflections, we have the load given and we want to identify what is the deflection at the tip. So we will solve the differential equations we have, and this equation has both the components of u2 and u3 together in this equation because it's a non-symmetric cross section, so we cannot decouple the two directions, u2 and u3. A shear force will cause bending in both the directions, right? If you want to decouple this, you can evaluate the principal axis of bending frame and then write these equations in that frame. Then you will be able to have an equation with just u2 and an equation with just u3 and solve the equation. But then if you want to represent your answer, you have to come back to the frame of reference which is given in the problem, right? You cannot just calculate everything in the principal axis of bending frame and leave it there, because then the user doesn't know or the engineer doesn't know what frame of reference you chose. He cannot visualize the frame of principal axis of bending. He can only see, okay, this is I1 and this is I2. So you have to rotate it back, all the results. And then you have standard boundary conditions and slope. Slope is 0 for a cantilever at the root, and the moment and shear force boundary conditions on the right end, right? Because it's a free end other than the load P. So then you'll evaluate these displacements and you'll receive a plot like that, right? Because it's an unsymmetric section, so it has both u2 and u3, so it's like a 3D plot. If it was a planar problem, you would have just got bending in x2 or x3. Okay, so I think, yeah, go ahead.
So we will have to solve differential equations on the exam?
No, there won't be any deflections.
Okay, so this deflection...
Yeah, it's just for, I just wanted to give a closure to the problem
Okay.
and explain, yeah.
Thank you.
How many problems are on the test?
I don't know that. Yeah. But you should be quick when you solve problems. Yeah.